Math 2414, Calculus 2. Calculus 1 review. The chain rule, part 1. It's been a long time coming, but in the first 5 videos in this series, we reviewed, 28 derivative rules, I think? The last 6 of which may have been unfamiliar if you're not familiar with hyperbolic trig functions. To be honest, there were 6 more we could have done, which was the derivative of inverse hyperbolic trig functions, but let's just say that we've reviewed enough derivative rules. But there's one more we need to look at, and that's the chain rule, which basically says we can take the derivative of anything, no matter how big and chunky the function is. Don't be intimidated by the part 1 and the part 2. The part 2 is just more examples. But let's get right to it. The chain rule. The chain rule says how to take the derivative of a function that is the composition of 2 other functions. In other words, if you have one function inside of another, in this case f of g of x. And by the way, this can also be written using composition notation, saying f of g of x. The definition of f of g of x is literally the same words, f of g of x. But I will probably refrain from using the composition notation because most of our functions are just going to have things already written inside of them to begin with. But I digress. If capital F of x equals f of g of x, then the derivative of capital F of x is the derivative of f of g of x times the derivative of g of x. This is the standard derivative of the outside, derivative of the inside protocol for the chain rule that says to take the derivative of one function inside of another, you start by taking the derivative of the outside, you leave the inside alone, and then you multiply times the derivative of the inside. Now, one thing I will do regularly, and this is my own personalized notation, is that when we are executing the last part of the chain rule that says times the derivative of the inside, I will frequently double underline the inside before it gets differentiated, and then point it to its derivative as the conclusion of the chain rule, as you'll see here in a moment. So again, the chain rule basically says if you have one thing inside of another, to take its derivative, take the derivative of the outside piece, leave the inside alone, then multiply times the derivative of whatever was on the inside. Let's take a look at 3 examples, and then I'll do another video with 3 more complicated examples. Find the derivatives. A, f of x equals the square root of x squared plus 1. Now, before we jump into the chain rule, there's something that you should already be familiar with, but if not, then you're about to become re-familiar with. You don't do calculus to radicals. You don't do calculus to square roots, cube roots, etc., etc. Well, you can, but we don't have rules for them because we don't need them. Do you remember how to take the derivative of a square root? The answer is you rewrite it as an exponent. So, before we take the derivative, we need to do some algebra up front, which is to rewrite the square root as a 1/2 power. If you need a review of radicals and exponents, let me know. I can link you to a video that I made for my college algebra classes. But I digress. Before we take the derivative, we need to write it as an exponent because we have a derivative rule for that. So how do we take the derivative of this? Well, the chain rule says you take the derivative of the outside. The outside is a 1/2 power, and for its derivative, we use the power rule, which says bring down the power and then subtract 1 from it. So there's the quote-unquote derivative of the outside. And if you're like, wait, where'd the negative 1/2 come from? Because that's the answer to 1/2 minus 1. Chain rule also says leave the inside alone for a moment. So the inside is left alone. But then it follows up with the derivative of the inside. And so now we have to multiply times the derivative of the inside. Well, the derivative of x squared plus 1 is just 2x. And I hope that doesn't need explaining why the derivative of this is 2x. At this point, we technically have our derivative, but we owe it to the problem, and this is going to be something I expect you to do, to simplify your answer as much as possible. And another personal preference of mine is if you do some algebraic shenanigans at the beginning of a problem to make it easier or flat out doable, I prefer the answer to have the same structure as the problem. This problem started as a square root, not as a fraction power. I would like for it to end as a square root. So we have some things we need to fix. Let's take a look at them. We got a bunch of things multiplied, and we have not only a fractional power, but a negative fractional power. Negative powers reciprocate things. So I'm going to set up a big fraction and figure out where everything goes. This 1/2 is just that, 1/2. This parentheses having a negative power is going to get shipped to the denominator, because that's what negative exponents do. It's not wrong to leave it up there, but there might be a benefit to moving it downstairs, namely not having a negative exponent anymore. The contents of that parentheses would stay the same. So in the denominator we have x squared plus 1 to the 1/2 power. As far as the 2x, there's nothing reciprocating it to the denominator, or equivalently you could view it as over 1, which means it was in the numerator the entire time. So the 2x is in the numerator. All right, so we've combined it into a single expression, single fraction, and now let's just see if there's anything we can clean up. There is something we can cancel, the 2's. The rule for canceling in a fraction is straightforward. If you're part of a multiplication problem, you're eligible to cancel. This 2 on the bottom is, so is the 2 on the top. I know it's got an x attached to it, but that literally means 2x, 2 times x. So these 2's do cancel. We can do 1 times x to get x, and we can turn the 1/2 power back into a square root. So if this were a homework question or a test question, this is the answer I hope you would get to and stop at. Now, like I said, it's not technically wrong if you leave the 1/2 power instead of rewriting it as a square root, but as a test question, I would explicitly say in the directions, write your answer using radicals because it started that way. So this is a good place for this problem to stop. It's starting to sound like Michael Penn. All right. So yeah, chain rule. Do it and clean your mess up. Let's take a look at B. I'm going to move these over a little bit, but as I'm moving them over, you might be thinking these are the same problem. They are not. They both have sign, they both have x, they both have an x cubed. But why are they different? It wasn't actually a rhetorical question. How are these two problems different? Move this over a little bit. If you were trying to describe to somebody the biggest difference, what would it be? The biggest difference is who has the exponent. In example B, the exponent belongs to the x, but in example C, it belongs to the trig function. In other words, sine cubed of x literally means sine of x cubed, and it's important, it's critical, when you're taking derivatives of trig functions with powers to know who has the power, because when you execute the chain rule, you have to know when it's time to take the derivative of that power, whether it's on the outside or the inside. In example B, the power is on the inside of the trig function, so when we take the derivative, we will start on the outside. What's the derivative of sine? Cosine. Chain rule says derivative of the outside, leave the inside alone, so leave the x cubed alone, then follow it up with the derivative of the inside. Remember, I'm using the double underline and the arrow to say I am now multiplying by the derivative of the inside. I am now finishing the chain rule. The derivative of x cubed is 3x squared. And then, of course, look to see if you can clean up this answer. There's not much you can do here, but there is something I would strongly recommend. If a student sees this, they might be inclined to multiply them together to make 3x to the 5th. Do not. This x cubed is inside the trig function. This 3x squared is outside of it. And in general, things outside of a function cannot be combined with things inside the function, so don't put these together. And I would not leave it at the end. I would not leave the 3x squared at the end, because when you put something at the end of a trig function, you might accidentally want to put them together, especially if you don't write parentheses. Because if you didn't, you're going to be real tempted to put these together, which you shouldn't, because again, the x cubed is inside the trig function, the 3x squared is outside the trig function. So even though the answer is perfectly correct and there's not really anything else we can simplify, a good rule of thumb is if you can avoid it, do not write things after trig functions. Or rather factors, I should say, things multiplied. If it's a product with a trig function, put the trig function last and the rest of it first. I think, and pretty much every other mathematician would probably agree with me, that the best looking answer for this derivative is 3x squared times cosine of x cubed. One way you can bypass that is that when you do the derivative of the inside, put it in the front. You may not have space over there depending upon how you've written it, but there's nothing wrong with putting it in the front. All right, let's take a look at C. F of x equals sine cubed of x, which, as we've already discussed, means the cube of sine of x. The reason it's critical to note what that cube means and where it's located is that when you do the chain rule, you have to know who's outside and who's inside. In this one, the outside was sine and the inside was cube, but it's completely reversed here. The outside is cube, the inside is sine. So what would this derivative look like? Well, just follow the chain rule. Do the derivative of the outside, the derivative of the cube, you bring down the cube and you lower the power to square, leave the inside alone, so the inside is sine of x, but then the chain rule says times the derivative of the inside. Derivative of sine of x is cosine of x. Is there anything we can do to clean this up? Well, not really. The constant is in front, like I moved it over there. We do have something after the trig function, but it's another trig function, so somebody's got to be after somebody. Really, the only thing we could do is rewrite the sine, the square of sine is sine squared. And that is considered standard. To rewrite sine, the square of sine of x is sine squared of x. In fact, most teachers would say, don't write this, just write that, and I'm one of those teachers. Now, could you have done this derivative without literally rewriting sine cubed of x as the cube of sine of x? Yes, you could. As long as you stay cognizant, as long as you remain aware of who is the outside and who is the inside, it is not necessary to rewrite this as the cube of sine of x. You could just say, power rule, leave the inside alone. But the problem with this is that it's not immediately clear what the inside of the power was, because if I double underline that, it looks like I'm underlining the square and I'm not. It's the derivative of sine of x, which of course is cosine of x. So we get the same answer as before, 3 sine squared of x comes cosine of x. But if you want to play it safe, I would rewrite this as the cube of sine of x. So that way it's explicitly clear what's inside and what's outside. And when you execute the chain rule, you do it in the correct order and you take the derivative of the correct inside. In the next video, we're just going to look at a few more examples of the chain rule and then we'll move on to another topic.